Okay, just testing the laser. Okay, hello everyone. My name is Christine. I'm from the University of Melbourne. And just to clarify, that is neither Jade nor Bernard's university. There's 3 universities in Melbourne. I work directly with Meg Millhouse and Andrew Malados, who were my PhD supervisors, and of course Marek and Tamaya as well for the CWB side of things. So today what I'm going to talk about is this thing called a dedicated frequency analysis, which I think we've seen a couple of flavors of this earlier this week. We've seen some from Coulter looking at match filtering searches for low frequency features. We've seen some from Alejandro, where he looked at the slopes to probe the EOS, and then just from Adrian on like cross correlation for low frequency features. So that's kind of like the same idea. I'm going to present something like this, but in a different flavor, in a Bayesian way. So just an overview of my talk. I'm going to kind of recap the signatures of core collapse supernova. I think people are really sick of hearing this at this point. And I'm going to introduce this framework that me, Marek, and Tamaya have been working together with over the last year. And then we're going to talk about the different analysis pipelines that are used in here. You may have heard of these 2 names across the week as well. The use cases of this sort of framework and the applications and the results that come out of it. So, yes. Oh, okay. I'm so sorry. Did that? Yeah, did that work? What was that button for? No? Maybe? Okay.
Yes, it was another one.
What about now? Yes? Okay, excellent. All good? Okay, so yeah, we've seen this a lot earlier this week, that the gravitational signature of supernovae can be divided in broad terms into 2 different categories. So we've got the high frequency, we've got these like PNS oscillations, and which we use this to probe the equation of states, right? And then there's the other part, which is the low frequency, where we see like these sort of hydrodynamic instabilities, SASI, like neutrino-driven convection. So this is actually the feature that's going to be the focus of this talk, because what we're trying to do with our pipeline is to potentially be able to constrain the explosion models if we were to make a detection of a supernovae. And the other thing that's nice about this low frequency band is actually it's within the most sensitive region of the LIGO detectors. So you can see the noise floor here is the lowest compared to the rest of the detector frequency. Okay, so just to kind of give you an idea, this work is actually inspired by Marek and Michele's work on, I think Michele has shown a nice plot in his talk about how they looked at the reconstructions in different frequencies, and then they come out with different overlaps and different accuracies. So that's kind of inspired by this work, where so essentially we're cutting off the signal, we're slicing the signal, which is on the left-hand panel, we've got the full signal. So there's just a single example of it, the SFHX signal, so the 15 solar mass model, S15, you may have heard before. We're slicing them into this high frequency region and this low frequency region, and we're constraining this low frequency between the 32 hertz and 256 hertz. So 32 hertz, because anything below that has too much noise in the noise floor, so we don't really trust much of that. So that's why we constrain it to this band. Okay, so the 2, all good? Yeah, so the 2 analysis pipelines that we're using in this work is a coherent wave burst, which you'll hear a lot more from Sergey tomorrow, but just in a very quick 1-minute summary, it uses this cross power and excess power statistics to tell us whether or not something in the data is sort of consistent with a signal. And specifically that detection statistic scales with the coherent network SNR of your detector network. So that you're going to see that as this eta here throughout the talk. And the next pipeline that we're using is BaseWave. You may have also heard of this before. So this is a fully Bayesian pipeline. So essentially how BaseWave works is we try to reconstruct the signal from ground up as well, much like CWB, but instead of using just sort of a multi-resolution wavelet transform, we're trying to fit sine Gaussian wavelets into the data. And the parameters of these sine Gaussian wavelets are fully sampled using a transdimensional, so a multi-dimensional Monte Carlo Markov chain sampling. So which means all the intrinsic parameters of time, frequency, amplitude, and so on are directly sampled from this MCMC. So that's why BaseWave is actually quite computationally expensive. But the good thing that comes out of it is we get to do a model comparison between a signal and a glitch model. And that detection statistics that's unique for BaseWave is that it doesn't directly scale with just the signal to noise ratio. It also scales with the model complexity, which gives us this extra layer of telling us how sure we are that this is a signal or a glitch. So kind of the reason that how we kind of arrange these pipelines is we're using coherent wave bursts to do this fast and computationally efficient analysis of the full data set, so of the background of all the supernovae injections. And then essentially what CWB does is it identifies events that are eligible for this follow-up framework that we're proposing. And this follow-up framework is then conducted using BaseWave. So BaseWave also does its own independent analysis of this full band, so 32 hertz to about 2000 hertz. And then it does this other follow-up where it slices your signal into two parts. So that's what we call the dedicated frequency analysis, or if signal processors are here, it's called a bandpass analysis. So you'll see them as referred to as low frequency LF and HF analyses. Okay, so the use cases, I'm sorry that's blocked out, but that says use cases. So the use cases of this dedicated frequency framework is to detect and characterize signatures of core collapse supernovae that has already been detected. So we're not really trying to reinvent the wheel. We're not trying to reinvent a detection benchmark or whatnot. So let's say if LBK finds something that is 1 per 10 years and they're like, okay, that's a pretty good detection, then we'll follow up on this kind of events. That's the purpose of this analysis. So that's essentially, that's why we put the CWB first, because that's what LBK uses as like kind of a burst detection benchmark algorithm. So the workflow goes like, we've got CWB doing the full band analysis, so analyzing the full signal, and then we identify candidates with false alarm rate of less than 1 per year. So I know this constraint is not very strict, is a lot more lenient than the ones you see in the burst, LIGO burst paper. There might be like 1 per 100 years, or some people use 1 per 10 years, but we're just kind of using this so we can have like a good amount of signals to follow up with this dedicated framework to prove that it's useful. And then so after these candidates have been identified, we've got BaseWave doing these different follow-ups. So BaseWave does its own full band analysis, like I said before, and then it also like does these low frequency or high frequency analysis depending on what we need. Okay, so the first part of my results, of our results, is to look at how this sort of dedicated frequency analysis can help us constrain core collapse supernovae models, specifically looking at SASE and neutrino-driven convection features in the spectrogram. So what we have here is a list of models. So I know this list of models is not as comprehensive as Adrian's. This is there's two reasons for this. One is because like nobody has really tested this method. We don't really want to inject 20 waveforms and not know like what comes out of it. So we are very careful in terms of selecting our model. And second is that BaseWave, like I said before, is very computationally expensive. So it's not really worth it to analyze this many signal, not knowing what the results are going to turn out to be. So we've selected our waveform models based on the SN 2023 IXF paper. So that's the one that Yan Yan presented on Tuesday. And specifically, we looked at candidates which are, models that are non-rotating. They're all, of course, three-dimensional. And they're at solar metallicity. So this is just sort of based on my understanding is like the more common types of core collapse supernovae progenitors, so that's why we went for the non-rotating case. And the way we select these models are based on how much SASE is present in them. So topmost SFHX, or S15 as you will see it, has the most sort of like low frequency power. So on the right column here is just showing you how much of this low frequency power, so anything below 256 hertz as a percentage of the full signal. So you can see the SFH, which has the softest equation of state, has the highest low frequency power here, and it kind of goes down so kind of like essentially the top 4 models has some sort of SASE, and S18 has very, very minimal SASE. So I think Jade showed me a spectrogram that there was like tiny bit of SASE in the spectrogram, but like I think we just consider it as it has little to none. Okay, so just to kind of give you an idea of what these models look like, so I didn't show all of it because it can't fit in a slide. So essentially SFHX here. So all of these are actually plotted on the same time scale. So as you can see, like all the time axes are the same. So this is kind of just to show you what the duration of these signals are like. So for SFHX, we can really see this low frequency feature being really dominant here. So that white line is just kind of, sorry, my laser pointer is not really going in a straight line, but yeah, that white line essentially is just showing you where the cutoff for the low frequency analysis is. And just for this particular signal, we're just showing you what the percentage of the low frequency content is. So just to highlight actually these numbers on this right column, is calculated by averaging over 175 models injected at different like orientations and different sky locations, just so we kind of get a general idea of what how these models behave overall. Okay, so yeah, and then we can see the S25 also has, S25 also has kind of this low frequency feature, and then S18, there's still some kind of low frequency stuff, but not as prominent as the ones in SFHX and S25, so just to give you an idea. Okay, so background measurements, we've heard from Marco Drago earlier today on what false alarm rates are and how we calculate them, so I'm not going to go into too much detail on that, so you can go back to his talk and have a look there. So on the left-hand side, we've got the false alarm rate measurements from CWB, so we've got the false alarm rate versus that detection statistics at coherent SNR that I was talking about earlier. So you can see, like, of course, at higher SNR, there's lesser of these noise candidates. So this green line here is just indicating where false alarm rate of 1 per year is. And so Bayes wave only follows up anything that is kind of has a significance greater than this, so anything below this green line, because like I said before, Bayes wave doesn't have that computational capability of following up thousands and millions of signals. So like, because we only care about signals that are more than 1 per year false alarm rate, so that's what we follow up in the background for Bayes wave. So in the Bayes wave case, so actually in previous work, we've shown that this method actually, like a Bayes wave and CWB like implementation, actually improves the false alarm rate because, of course, because we only follow up a part of these background signals. So kind of like this joint implementation has been beneficial and has been used in the all-sky burst paper as well. And so the Bayes wave background looks something like this. Sorry, my laser pointer has disappeared. Yeah, it looks something like this. So that pink line down here is the full band analysis. So we're looking at the 32 to 2000 hertz analysis. And then the purple band is the low frequency. So you can see like that the false alarm rate has decreased by quite a bit when we limit this analysis band from 32 to 256 hertz. But what I want to point out is that this base factor between these two are actually not directly comparable because they are looking at different sort of parameter spaces. So really, we take this with kind of a pinch of salt, but because we're comparing the false alarm rate, we don't look at the base factor. We look at what the false alarm rate is at a given base factor. So let's say if you say, I have a base factor of 10 for low frequency and a 10 for high frequency, it doesn't mean anything unless you count them in the background, okay? Okay, so now to how we inject these supernovae signals, we're also quite careful about it because we don't want to be injecting things that cannot be detected. So what we do, like I said before, the dedicated frequency framework only follows up signals that have been detected by the standard detection benchmark, right? So what we do is we use CWB to determine this HRSS 50. So HRSS 50 is the HRSS at which 50% detection efficiency is achieved. And then, yeah, Bayes wave then only follows up injections with this false alarm rate. There's a pointer has disappeared again, like with false alarm rate of less than 1 per year. So this just kind of shows you like how the efficiency curves goes. And then that line here is the 50% efficiency. And this numbers in these brackets here are the HRSS that we measured. Then you might also wonder at what distances are these HRSS injected at, like how far out we can detect each of these models. So really the equation that we use to calculate that is this top left equation here. So R is the distance. So these are just constants. And we've got the HRSS, the F naught, which is the central frequency, and the energy of the gravitational wave. But here we assume that the central frequency is roughly equals to the peak frequency. And then we use that to calculate what the distance at this 50% detection efficiency is. So the top panel here is our results. So we've got the SFHX, S25, and so on. And bottom panel here, I just copied like the relevant bits of the table from the O3 optical search by the LVK collaboration. And you can see that the numbers are quite consistent. So like S15 is all about 6 and 7. We've got 7.8 here. So S15 is SFHX, and then 25 we've got 4.9. Another thing about this to prove a point is that in our search we use an all-sky method to study these supernovae, whereas in this paper here they used a targeted search. So I think Jade mentioned that, and Amaldi, someone did. I think it was Francesco who did a study on whether all sky is better than targeted or vice versa. And he found that the targeted search improves the detection sensitivity by a little bit, but I guess is not too much. But I guess in this case, we're actually showing that in some cases, like for example here, we can detect S25 to a larger distance, but not by a lot, by a slightly larger distance if we use an all-sky search. So really, what I'm trying to show in this page is it doesn't matter if we use an all-sky search or an optically targeted search. And the good thing is they're quite consistent. Okay. Okay, now to the results. So on the left-hand panel here, we've got the detection efficiency. So we inject 175, we use 175 waveforms for each of these. So essentially, CWB finds more than 175 candidates with this false alarm rate that can be followed up. But for each of these models, we select 175, and then we run Bayes-wave on them, and then think about, what is the efficiency of detecting these 175 signals with the different types of analysis. So as expected, so in the pink crosses on the top there, these are just the full band analysis. So Bayes-wave also detect all of these to 100% efficiency. So whatever CWB finds, Bayes-wave finds. So great. Now let's look at the purple line, which is the low frequency analysis. So of course the detection efficiency is not going to be perfect because some of these signals don't even have prominent low frequency features. So all we'll see here on the x-axis is the average low frequency power in each of these models, and we can see that at the higher, so this is kind of like going the other way around. So from left to right, we're decreasing in low frequency power. So on the left, we obviously have the highest low frequency power, and that's where SFH lies. And we can see that the detection efficiency is quite good for this type of signal. And as we move to the right of the panel, the efficiency starts to decrease. And when we get to S18, where the SASE and neutrino-driven convection features are not really prominent in the spectrogram, we don't really have good detection efficiency for this. So then you might ask, well, we don't really have like a detection efficiency plot in a real scenario. So we also redid this in terms of the false alarm rate. So each of these data points here are just the medians of the 175 signals that we injected. The crosses are for the full band analysis. So you can see all of them fall below that line, so which means all of them are detected, as this plot says. And then the triangles here are for the low frequency analysis, where we can see, again, moving from left to right. So just because there's two types of data that we're showing here, so we kind of just make this axis equally spaced for your convenience. So yeah, you can see as we move from left to right here, we can see that the false alarm rate starts to increase, right? That means the less low frequency power we have, the less likely we have this, thank you, we have these sort of detections. So, okay, I'm going to skip through this, but I was going to just kind of quickly show this as that discussion where we talked about, low SNR, what's the SNR of detectable SNR. So whoever asked that question is welcome to speak to me later. I can show you this plot again. So I'll skip that for now. And so the implications of our results is really saying that core collapse supernovae models with higher low frequency content has this better detectability with this low frequency follow-ups. But this sort of LF detectability is not guaranteed. So as we saw before with the spectrograms, S25 and I can guarantee you as well, D15 and MESA 20 has some sort of SASE, but they're not always detectable. So what does this mean? It means that a successful low frequency detection is actually useful for constraining these explosion models. But if there's an unsuccessful detection with this sort of follow-up analysis, then we can't really make a conclusive kind of statement of whether or not low frequency exists. Okay, so just to kind of close this up, in fact, the dedicated frequency analysis is not limited to this low frequency analysis. We also can use it for, we can choose a band that we're interested in and look at it. So this is really just like a demonstration of how we can use it otherwise. So what we've done here is looking at whether or not the counterpart of the low frequency, the high frequency component, can be used to enhance detection. So how we're doing that is we actually picked the loudest trigger from, the loudest event associated with a core collapse supernovae from the 03 optical targeted search paper. And the reason why we chose this event is because it has the lowest false alarm rate, which is still pretty high, but it has the lowest false alarm rate, so it's the most computationally efficient for Bayes-wave to follow up. And the other interesting thing about this event is that the reconstruction of CWB and Bayes-wave shows absolutely no signal power below 256 hertz. So what we're doing here is that we're saying we know that there's no power below this certain frequency. So what if we limit our analysis, just telling these algorithms to look at everything above 256? Can we enhance the detection significance, or can we lower that false alarm rate of this event? So the answer is yes. So just here, we've just copied some of the results from the CWB side. So this is from the optically targeted paper. So the false alarm rate is 22.1. And then when we run Bayes wave, and because we're doing that follow-up again, we only follow up events with false alarm rate less than 22.1. So Bayes wave obviously has a lower false alarm rate, but by quite a bit. It's now dropped down to 6.4. So that's almost a factor of 4. And then if we then constrain our analysis to just the high frequency, so saying we completely ignore everything under 256, thank you, and we ignore everything under 256, then we are actually reducing this false alarm rate a bit more, because, and that we're not cutting out any signal power. We're just literally telling our algorithms to look where the signal is. So that's great news. And this is a potential application, another application of the dedicated frequency framework. But obviously the aim of that was to constrain the explosion models to begin with. So this is kind of like something that came out of it, like a secondary thing that came out of it. So just to summarize, we've demonstrated in this work the applications of our dedicated frequency framework, which is a hierarchical pipeline that uses CWB to search for eligible candidates and then use Bayes wave to follow them up using its own full analysis and then sort of these bandpass analysis. And so I have a few, so inspired by Marek's talk, actually, I have a few questions for the crowd. Is can we potentially also then tune CWB to perform this sort of dedicated frequency framework on its own without Bayes wave, and then having these two results agreeing with each other, we have more confidence in our results. And the second point is, can we repeat this analysis for like high frequency, looking for high frequency features? Is there a certain type of frequency features that this group is interested in? So if you have any opinions or suggestions, we're very happy to hear them. So yeah, I'm going to end my talk there. Thank you very much.
Thank you, Christine. Are there any questions?
Thank you, Christine, for your talk. I have a question about your false alarm rate. I mean, for the low frequency and high frequency, you have shown that your low frequency false alarm rate distribution is well reduced compared to the full band. But usually, I mean, we expect more glitches, and especially high amplitude glitches at low frequency. So for me, it's a bit counterintuitive, your distribution. I was expecting not such a big difference between the low frequency and the full band.
Okay, so thank you for that question. Hopefully people can still hear me. Thank you for that question. That's actually directly leads back to that unique feature that I was talking about in Bayes wave, where we don't just, the detection statistics doesn't directly scale with the signal to noise ratio, it also scales with N. So N here means the number of wavelets. So when we're looking at low frequency, we're really just looking at 32 hertz to 256 hertz. So the number of wavelets that it can fit in this small frequency range is not a lot.
So it's really the effect of the statistics.
Yeah, exactly. Yeah,
right.
Correct.
Okay.
So that's why the low frequency and high frequency has such a big discrepancy.
I think I got it. And then, you know, there's another thing about if you split your analysis in several bands, you know, usually what we do when we have several analyses, several search, we apply a trial factor to take into account that the fact that we have seen an event searching in the data with several pipelines, several searches. So we apply a penalty factor. And I would guess you would have to do the same thing if you start splitting Bayes wave search into several frequency band. You would have to take into account the fact that you are actually doing two searches. Okay, when you compute the significance of an event, because you don't know a priori if your event is at low frequency or high frequency, or you don't know where it is exactly.
Okay, yeah, I need to think about that. I don't have an answer for that for now. Yeah. Thank you.
More questions or comments? Well, then let's thank Christine.